AP Exam Review, Lesson 7. In this lesson, we'll cover the concept of equilibrium, an extremely important concept. In fact, the AP exam will definitely test you over this. This is one of the central ideas that is tested. So let's get started on the review. So we have a few multiple choice questions just around the concept of equilibrium. So we have 4 moles each of X and Y are placed in a 1 liter vessel and allowed to react at constant temperature according to the equation above. 6 moles of Z is produced, and what is the value of the equilibrium constant? So the central idea of equilibrium is this equilibrium constant. And remember, in general, it's set up as products over reactants, raised to the power of coefficients. And so what we need to do is find out how much we have at equilibrium. Very often you begin with an amount of reactants and then you wait for the reaction to come to equilibrium, and then you check those concentrations that result. So here, if you recall, we set up an icebox. I'm going to go ahead and do this without an icebox, just logically, but eventually we're going to use the icebox for this type of problem. What we're saying is that we begin with 4.0 of each of our reactants. Now, and nothing of the products, and then as the reaction proceeds, we lose reactants and we gain products, which means we'll end up with less X and Y at the end, and then with more Z. Now, it says that we have 6 moles of Z at the end of the reaction. This is 6.00. Realize that if the reaction were to go to completion, then you would completely react all 4 moles and you would get twice as much. You would get 8 moles. But because we have 6 moles, this shows us that the reaction does not go to completion. In other words, it's an equilibrium reaction. So what we have to find out is how much do we have here of both X and Y left. Well, because we produce 6 of this, for every 2 of Z, we lost 1 of Y and 1 of X, which means we must have lost, in the middle of it, we must have lost 3 here, because since we gained 6, half of that is 3, and then we must have lost 3 here as well. Essentially, this is the icebox. Even though I said we'll forego it, this here is your icebox, but logically understanding it is the first step. And so we end up with 1.0 of each of our reactants. And then we can plug this into the equilibrium constant. Our product is 6.0. Now remember, the coefficient goes up top, so we have 6.00 squared, and at the bottom we have 1.00 times 1.00, which essentially gives us 6 squared, which is 36. So E is the answer here. Now remember that the equilibrium constant could be expressed in terms of concentration, that we designated as Kc, and in terms of pressure, and that was Kp. Concentration, we usually put them in brackets, and pressures, we just put the pressure of whatever it is your product, in this case Z. So here we know we're dealing with concentration because it gives us liters and moles. So watch for this, but the expression is set up the same way. It'll always be products over reactants raised to the power of the coefficient. Let's try example 2. The equilibrium constant for the gas phase reaction above is 95 at 25 degrees Celsius. What is the value of the equilibrium constant for the following reaction at 25 degrees Celsius? Notice it's the same reaction but flipped and multiplied by 2. In fact, we had oxygen, half a mole of oxygen on the right side. The oxygen moves to the left and we have a full mole, which means we've doubled the reaction. So we've doubled it and we've flipped it. Now, when you flip a reaction, remember, since K is set up as products over reactants, when you flip the reaction, your reactants become products, and you end up with reactants over products in terms of the first reaction. So really, your K just inverts. And then if you multiply the coefficient by 2, remember the coefficients go in the power, which means our power everywhere gets 2. So since we begin with 95, we flip it, which means we get 1 over 95, and then we square everything. The whole equation gets multiplied by 2, so we would square both the top and the bottom. But 1 squared still gives you 1, so you end up as 1 over 95 squared for the new equilibrium constant. And that is actually hiding right below the pen. Right here. And that is how we solve that. How about for something next? It says, for which of the following reaction mixtures at equilibrium would reducing the volume of the container at constant temperature cause the equilibrium to shift toward the products? Now, if you recall, this is where we can adjust the equilibrium by putting some sort of stress on the system. And the idea was whatever stress we put on the system tries to undo the stress. In other words, if we increase the pressure, the system tries to reduce the pressure. If we increase how much product we have, the system tries to remove the product, and so forth. So we're looking for what will happen. We want to see one that goes to the products by reducing the volume. Now, anytime volume goes down, remember pressure goes up. This is Boyle's law. This is an inverse relationship from the gas law. And so, Boyle's law. And so, if you take a look at A, if you were to increase the pressure, because recall that solids do not affect equilibrium, and neither do liquids, it's all going to come down to the gas. So we have a mole of gas on the right side, and if we increase that pressure by reducing the volume, the system will try to reduce the pressure by shifting to the left. So this first reaction actually gets shifted to the left. So that's not what we're looking at. We're hoping to find one that shifts to the products, toward the products. Our second reaction, we have two gases. We have a mole of gas on the left side, and we have 2 moles of gas on the right side. Well, again, if we increase the pressure by reducing volume, the system tries to reduce that, and the side that has less pressure is the left side, so it'll again shift to the left. So that one won't do it. Part C, here we have 2 moles of gas, and also we have 2 moles of gas on the product side. So in this case, the system won't shift in any direction. It'll actually stay the same because there's no difference. This one can't be it. But if we take a look, running down all the way to E, D is actually in the same boat, so that's out as well. Taking a look at E, we have more moles on the reactant side, which means if we lower the volume, the pressure goes up of the whole entire vessel, and for the system to reduce that pressure, it will have to get rid of gas, and it can do so by going to the product. So actually E is the answer. This was called Le Chatelier's principle. The other thing we talked about in Le Chatelier's principle was temperature. So if, say, this equation B is exothermic, which means delta H is, with delta H is negative. Remember, if it's exothermic, we can think of heat as a product, which means if we lower the temperature, effectively we're removing heat, and the system shifts to the left to replenish that heat. Heat can also affect the equilibrium mixture. Usually reactants, products, pressure or volume, pressure through volume, and then heat can be adjusted. So review all those if you don't recall them. Let's take a look at a few more questions on the multiple choice side. It says the following 2 questions refer to the experiment described below. H2 gas and N2 gas were placed in a rigid vessel and allowed to reach equilibrium in the presence of a catalyst, according to this equation. So here is our ruling equation. Notice we have 2 moles on the product side. Altogether we have 4 moles on the reactant side. And the system is exothermic. The diagram below shows the, or rather to the right, it should be to the right, shows how the concentration of H2, N2, and NH3 in the system changed over time. So notice that we begin with 0 of NH3. Now NH3 is our product, so we begin with nothing of the product but a bunch of reactants. We just stock our container, you can say, with reactants. And as the reaction goes to equilibrium, the reactants, concentration of the reactants goes down, the concentration of the product goes up, which is understandable. Now, what happens here is equilibrium is reached or is defined whenever the amounts stop changing. remember, you'll still have both the reactants and the products at equilibrium. That's why you have both N2, which is reactant, you have NH3, which is a product, and you have H2, which is a reactant. Because equilibrium doesn't mean that all the reactants have been consumed, it simply means the change, it stopped changing, the amount stopped changing. So that's what it wants us to do. Which of the following is true for this? Essentially, here we see that we are at equilibrium. This position right here, we're at equilibrium. And then the right answer, let's see if we can find it. The concentration of N2 decreased. This is not true because N2 is actually staying constant. The temperature of the system decreased. This isn't true. We're not really checking for the temperature here, but since the reactants and products aren't changing, no more heat is given off anymore. The number of effective collisions between H2 and N2 was 0. This is not true because the reaction still keeps going, which means there are collisions. In an equilibrium system, you have both the forward and the reverse reaction still happening. So there are collisions, there are reactants being made, or products being made. The rates of the forward and reverse reactions were equal. This is the key. This is how we define equilibrium. Recall we said equilibrium, at equilibrium, the reverse rate of the forward equals the rate of the reverse reaction. And really, this is how we define equilibrium. Equilibrium is defined in terms of the rates being equal. One way to think about it, if you think of a bottle with some water in it, if you cap the bottle, remember we said that the evaporation still occurs, but condensation starts happening at the same rate, and in the end, you don't see the water level changing. It stays there, but in the whole time, both evaporation and condensation is still happening. This is a dynamic process. Just the amounts are now staying constant, and that's the idea. Let's finish up with this question, referring to the same diagram. Here it says more NH3 gas is added to the system at time T2, at this point right here, while the temperature is held constant. Which of the following will most likely occur? Now this is back to Le Chatelier's principle. Recall that our equation is H2 plus N2 is in equilibrium with NH3. And balancing the equation should give us 3 here. So essentially we're adding product to the equilibrium. We're adding more product, and the value of the equilibrium constant will increase as part A. The value of the equilibrium constant will decrease as part B. The total pressure in the container will decrease. The amount of N2 increases, the amount of H2 will decrease. So let's think about what will happen. So if you add NH3 to the system, then the equilibrium will try to remove NH3. And so by removing NH3, it shifts to the left. And as it shifts to the left, it actually creates more N2 and more H2. So D, the amount of N2 will increase, would be the correct answer. Now, the other answer here, the value of the equilibrium constant increases, the value of the equilibrium constant decreases. It turns out that the equilibrium constant stays the same. It's just that the ratios of the products over the reactants, the amounts change, but the ratio remains the same. So the equilibrium constant does not change. It only changes when temperatures increase. So if if temperature goes up or down, that is when equilibrium constant goes up or down. So temperature is able to affect it. And it depends on whether it's exothermic or endothermic. In this case, because we said delta H was negative, we are exothermic, so we have heat as a product. So if you were to, say, increase the heat, increase the temperature of the system then would go left. Let's go ahead and do this with red. If you increase the amount of heat in the system would shift left to try to remove the heat. and as it does so, it creates more reactants and less products. So our K being products over reactants, the reactant amount goes up and the product amount goes down. So in this case, overall equilibrium constant would decrease, but that's only the case when temperature is changed. And to remember this, essentially all constants are temperature dependent. That would be the all constants are temperature dependent. That essentially would be the rationale behind it, if you would. Alright, so that concludes this lesson 7. Go ahead and review some of these concepts in more detail, and we'll do, actually, we're going to do one more. Looks like number 6 is also with us, and then we'll finish up the, why not? This is a pleasant surprise. We have one more quick little equilibrium problem to do. So at 450 degrees Celsius, that should be degrees Celsius, 2 moles of H2, I2, and HI are combined in a 1 liter rigid container. The value of Kc is 450 at, the value at 450 degrees Celsius is 50. Kc, this is our K. Which of the following will occur as the system moves toward equilibrium? Now realize we have equal amounts. We have 2 of H2, 2 of I2, and 2 of HI. Now if we put these numbers into the equilibrium constant, and this idea was the reaction quotient idea, and it used Q instead of K before equilibrium, but it was defined the same way. It was defined as products over reactants to the coefficients. So if we plug in the current values, let's see what we get. Q would be, our product is 2, don't forget to square it because there's a 2 coefficient in front. Our reactant is 2 times 2, which gives us essentially 4 over 4. Our Q is 1. Now, looking at how Q is compared to K, when we're at equilibrium, our constant is 50. Right now our constant is 1, so our constant must increase. So K will increase, or rather Q, we should say Q will increase. The quotient, this ratio will have to increase. And the way it can increase is if we gain more products and less reactants, which means our equilibrium has to shift to the right to get there. So this is essentially a place we're not at equilibrium yet. We're just asking which way will the reaction go to reach equilibrium. And we can say that we'll get rid of reactants and gain more products, is the idea. So more HI would be the best answer, is the idea. And so we should consider this idea of reaction quotient as well. This is a way of predicting which direction the system will go to reach equilibrium. Okay, so this should conclude lesson 7 of chapter 4 of the AP review.